Hey there, awesome physics students. Let's talk about some of the properties of stress-strain curves. So to give us a concrete example to think about, imagine you have a wire and we're putting this under tension, and the wire has a cross-sectional area of A and a length of L, and when we apply this force, this gives us an elongation or a stretch of delta L. So I'm plotting the stress versus the strain here, and when you increase the applied force or the strain, you'll see that it increases with a linear relationship between the stress and the strain. At some point, though, when you continue to apply the force, it doesn't continue to follow a linear relationship. It begins to curve. And so this portion here where it's a straight line, that's called the linear region. And this point here where it stops being linear is also often called the proportional limit. Now it will continue to stretch like this, and if you release it, it will return to its original length until you pass a point called the elastic limit. And if you pass the elastic limit, then if you increase the elongation past that, then if you release it, then it won't go back to its original length. And that's some sense you've permanently damaged it if you pass the elastic limit. Now, this is a metal sample here, or metal wire. As we continue to stretch it, it'll continue to increase, but then at some point this will start to decrease in thickness. It'll start to get thinner in the middle, and that's called necking, and the stress, will actually decrease. That is, the applied force necessary to continue to stretch it will decrease. And at some point it breaks at the end there. Now this peak stress that it can take is called the tensile strength, or the ultimate strength. Sometimes it's called the ultimate strength. For our purposes, we're primarily interested in this linear region here where it behaves very much like a spring. Because these are completely proportional to each other, that is, the stress is proportional to the strain with a straight line rule, we can come up with a simple proportionality equation. That is, the stress is equal to some constant, we'll call that y for right now, times the strain, which is the increase in L over L. Now this proportionality constant is called Young's modulus, or sometimes you see it used as an E for elastic modulus. And the interpretation of that here would just be the slope of the curve, because that's a proportionality constant, right? It's the rise over the run. The way you can make this expression here look just like a spring is if you multiply both sides by the area, the cross-sectional area, to get force on its own. So if you do that, to get force on its own, then the area goes up top here, and so you have the Young's modulus times the cross-sectional area. And let me put that with the length too by itself, and then because I want to get the elongation or the delta L by itself. So now this looks very much like what we see for springs. For springs we have F equals K delta X. And so this portion right here, the Young's modulus times the cross-sectional area over the length, looks just like a spring constant. Now we don't usually prefer this. We usually prefer this formulation because this relates directly to this graph, and this graph is a property of the material only. It does not depend on the shape, the cross-sectional area, or the length, or other physical properties, physical dimensions of the sample. It only depends on which material it is. Is it copper, is it iron, or what? Maybe if it's a compound or an alloy. So this is the formulation that we typically prefer. But if this were the formulation that we use, this number here would be a very, very large number because it's a very, very, if it's like a spring, it's a very, very stiff spring. Okay? So see, these are the properties of stress-strain curves that you need to be aware of.